Good morning, everybody. Can you hear me? All right. All right, we got 9 o'clock. How's everyone doing? Are you staying warm today? Okay, so your professor biked to work today, so just saying.
That's really
It can be
impressive.
done. I'm kind of crazy. It's hard to believe 3 days ago it was, what was it, 100 or something? It's crazy. Last week, I think it was, may have been Friday. I think it was Friday. So I was working at home, doing a Zoom meeting. And have you guys had any weird things happening, kind of awkward things that have happened in Zoom meetings yet? No. I had a near miss. So on Friday, so I was working at home, pretty warm. I'm realizing, okay, I got to, quickly I had to like scramble. It's like I have to get on this executive call for COPD Gene, and nearly got on. I'm like, I should probably put a shirt on. And that really happened. I didn't actually do it, but I was like, at the last second, I was like, wait a second, this would look really bad. So that was a near miss, but fortunately I did get it together, got my shirt on, and joined the executive call. So, and today, I think I figured out how to record it. I pressed the record button and it seems to be working. So this lecture will be recorded. And I trust that you guys have seen the homework and all the stuff I put on Canvas. So I will have hour after this class, 10:30 to 11:30. I realize that I'm going to keep that for today. I realize that once a month I have a meeting, a conflict meeting, so I'm going to have to change that time, but that would just be once a month, so hopefully not that big of a deal. So we can talk about that today after class, and then Yanran has an hour on Friday from 9 to 10 a.m. as well. So have you guys started looking at the homework is a question for you? Okay, that's good. That's step one. You look at it, right? And then step two is you actually start to do it. So that's good. You did the first step. You started looking at it. There's some questions there that require some thought, and it's kind of a mixture. One of the questions is really kind of a theory review, going through expected value and covariance and correlation. So for those of you that haven't had the theory sequence yet, it may be, there may be a little bit of new stuff in there for you. If you've taken theory, then, it should be maybe more of a review question. But we can talk more about that later. So what I wanted to do today is, first of all, I just wanted to finish the slides from last time. And so we were talking about graphs, and we got through most of it, talking about different types of graphs for longitudinal data. And we got to principal components analysis. How many of you are familiar with principal components analysis? You've either used it or you've seen it. Just I see like 3 or 4 or 5. Okay, so for those, can anyone tell me, like, if you actually used it, what you used it for?
I have used
used PCA for dimension reduction. It's like while fitting different deep learning models, sometimes the dimensions are really so much, or some features. In my internship, I have used is like more than 1,000 features, so we have to reduce some extent. So for that purpose, I have used.
What features? What is the data that you use it for?
Uh, Features as in the columns, I can say different type of columns, and when we start to find the correlation, and there are other methods like RFE, recursive feature elimination technique, and PCA as well. So I think these are the two factors I have used.
Okay, so what is it genetic data or what? I'm still not totally clear
It's
on
a
that.
sensor data. It's a company data. It's like different shapes of sensor, and that can vary from time to time. So I can say it's a multimodal time series data.
Okay. Tell me one more time that you said census data?
Yes.
Census data.
Yeah.
Okay. Okay, so yeah, and that's pretty common, you know, to take a large amount of data and really, you know, with that kind of data, or it could be genetic data or data where you just have a lot of measurements on subjects and you want to reduce the dimension. You want to find out the strongest patterns in the data, and that's typically what PCA is used for. And factor analysis is related to that, which again, you may be trying to reduce dimensions in the data, but factor analysis more specifically, there could be latent variables or things that you're interested in that were unmeasured that you want to try to identify in the data. So these two techniques, you know, are commonly used for data dimension reduction. But what I'm going to show you here is that we can actually use PCA as a tool a graphic tool to better understand the data. So basically, if you have a number of variables, and I'm assuming you guys can see the slides here. Let me just move this. So you have a number of variables. So pen is a little weak today. Okay, that's better. Just have to press down a little bit harder on it. Let's get rid of some of this junk here. So you have a number of variables, y1 to yr, and you're assuming those are normally multivariate normal with some mean and some covariance matrix. So the covariance matrix sigma, you can partition that into P times lambda P transpose, where P is going to contain the eigenvectors, and lambda are going to be the eigenvalues. Okay, and I think in math class, like a number of you, I'm assuming you've had math classes where you learn about eigenvalues and eigenvectors, and they could have different interpretations, but in terms of principal components analysis, the eigenvalues are going to indicate the magnitude of the variances of the principal components, and the eigenvectors are going to indicate the direction of the principal component. So what is a principal component? It's just a linear combination of these original variables. And the first principal component is a linear combination of the original variables that maximizes the variance in the data. And then the second one is the next most, capturing the next most amount of variability that's orthogonal to the first principal component, and so forth. So you actually create the same number of principal components as the number of original variables in the data, but you're hoping that a small subset of those principal components can capture the majority of the variance of the data. Okay, so what we're going to do, I'm going to show you how you can apply principal components to a data set with 2 variables, which would you do that for data dimension reduction? No. If you only have 2 variables, that's not a lot of variables, so you don't really need to use it for data dimension reduction. But I'm going to show you just how to use it in a graphical sense. And I think it also illustrates how PCA works too, when we just have a couple of variables. So we're going to look at the aspirin data where we're measuring ENO, exhaled nitric oxide. So that's going to be higher when subjects have more inflammation. Okay, so these subjects have, they're sensitive to aspirin, and so we're going to challenge them by just giving them a little bit of aspirin and then see how that affects their ENO levels. And so before, we have pre and post measurements here. So Y1 is the pre-measurement, Y2 is the post-measurement. And we're going to see what happens after the challenge, what happens to their ENO levels. So our first principal component turns out to be 0.5 times Y1 plus 0.86 times Y2. So we've taken a linear combination of the original variables and created this new component that captures the most variability in the data as possible in one variable, in one component. And then the second one has to be orthogonal to the first, and that's why it becomes negative 0.86 Y1 plus 0.5 times Y2. But the first principal component, if you take that eigenvalue and you divide by the sum of the 2 eigenvalues, it's about 98%. So you can see that most of the variability in the data is captured by this first principal component. Okay, now let's look at the graph here. And you see, so we have, so this is Y2 here, and this is Y1. And so I'm just plotting Y2 versus Y1, the post-measurement versus the pre-measurement, okay? Now, if you look at the data, where would the most variability, if you had to pick one line, what would that look like with respect to the scatter plot? Yeah, go ahead. Swanshu?
I'm thinking we can make a straight line from 0, 50, 100, like the dots we can connect.
Pretty much connecting the dots, that's right. So
yes. But
not quite like that, but this is really hard because I'm not drawing on, but it goes through the points, more or less like that, right? That's going to be the dimension that captures the most variability in the data, right? So that's our PC1. And then PC2 is going to be orthogonal to that. Okay. Now here's a question for you. You know, another place you kind of see this is in regression, right? Where you fit a line to the points. Would you expect the regression line to look like PC1, or would it look a little bit different than PC1?
I think PC1 is to some extent similar to the regression line, but it should be different, right?
It's going to be a little different. You know, it's true that it's also aiming to fit the points, right? But it's going to look a little different. So does anyone have an idea?
Is it because you have to have some points above the regression line and some beneath the regression line?
Yeah, you're kind of onto it. You know, the name regression, what does that mean? Regression to the mean, right? So the regression line is not going to be as steep. Okay, it's going to be pulled down a little bit relative to the PC1 line. So it's gonna be more like, I don't know exactly, but it's not gonna be as steep. So the regression line is probably gonna look something like that. Okay, it won't be as steep as PC1. It may not be quite that flat, but that's just a relative line that I drew there. Okay. So the PC is will go through the points. The regression line is going to be attenuated a little bit relative to that. Okay, so and here's a better a better drawing of PC1 and PC2. Okay, so what we can do is we can go back. I'm just going to run back real quick to these equations for PC1 and PC2. How, this is what we do for principal components and factor analysis, is we try to interpret what they mean. Okay, PC1, you're taking a weighted average of the pre and post measurements. So essentially, it's an average. It's like you tend to have lower ENO or higher ENO, and it's true that it's weighting it more to the post value because there's more variability in the post data. But essentially, it's an average. Whereas PC2 is differentiating the pre and post measurements. And so on this next slide, I interpret those. PC1 is a weighted average of ENO, the higher weight given to the post measurement since it contained more variability. So I call it an average component, whereas the PC2 differentiates the pre and post ENO values. Subjects with relatively low values did not react as strongly to the aspirin challenge, where subjects with higher values had post measurements that were much higher than the pre measurements. So I call it the reactivity component. Let me explain that in a little more detail. If we take we actually make a scatter plot of PC1 versus PC2. This is what it looks like. And here you see 2 points that really stick out, okay, whereas most of the data is here. So the question is, this subject just tended to have a higher value. So they had a higher PC1 value. So their ENO just tends to be higher, okay, in general. Whereas this subject here, they have an unusual value for PC2, okay? And if you go back and you look at their actual data, their pre-measurement was 80.5 and their post value is 79.1. Why is that unusual? It's because they didn't really react to the aspirin challenge. So they were a low reactor, right, relative to the other subjects. And that really stands out when you plot PC1 versus PC2. If you go back to the regular scatter plot, though, it really doesn't stick out as much. It's actually this value right here. Okay, let me circle that. So you can see when we plot PC1 and PC2, we're basically tilting the graph and actually flipping it as well. So it's tilted, it's stretched, and flipped. But we're really graphing the same data. So what we're doing is allowing us to see the data in a different way than what we would have been able to see. Okay, so that's sort of an unusual application of principal components analysis, but it's a graphical technique, and we're just trying to identify patterns in the data. Really quickly, I just want to mention one other data set, and this is one that you guys have seen, the ramus data. So this is the size of the ramus bone in the jaw measured for boys at 8.5, 9.5 years. So we can apply principal components to that data as well. We have those the 4 height measurements at those 4 time points. And you do principal components. You can do it in SAS, you can do it in R as well. Here are the eigenvalues. What do the eigenvalues tell you when you look at those numbers? So here are the eigenvalues. Keep hitting that button. And then here are the proportions. Can somebody tell me what that data is telling us there?
The first principal component explains most of the variability, 92% of the variability.
Good. Yep, that's what that's telling us. So it's telling us that most of the variability can be captured in one component, one linear combination of the original variables. Okay, now look at the eigenvectors down here, and can you interpret what that first principal component means? You can get somebody else jump in.
It's pretty much just an average of the 4 measurements across all of the time points.
Yeah, that's exactly right. So, and it's pretty close, really. I mean, even more so than that first application I showed you. This one, they're really pretty close to 0.5. So, you know, if we scaled that, if we divided again by half, then it would really be a true average. But it's essentially an average, right? It's just multiplied by 2. But really, you're taking an equal amount of the 4 measurements and getting a total amount, right? So it's just a scaled average, right? That captures the most variability. So it's just saying, you know, a kid that's larger in size, they're going to have a larger ramus bone probably, right? Or you could be small maybe and just have a big big jaw. It represents an average. Okay. Here's see if you maybe dust off your 6612 skills here. Look at the PC2. And it captures about 6% of the data. Any thoughts on that one? What that's telling us? Do you guys remember polynomial trends and the coefficients what they would look like if you have 4 time points? Did you guys talk about that at all? If you didn't, then this will probably be a little difficult. But if you did talk about polynomial trends and the coefficients that you would need for polynomial trends, then this should be a review. Do you guys talk about that at all in 6612? Coefficients for polynomial trends?
We did a little bit.
Okay.
This looks fairly linear.
Yep. Yeah, so for 4 time points, do you guys, Carrie, what would the coefficients be? Do you know what?
I don't remember exactly. I just know they make a line.
Well, your answer is pretty good. So if you have 4 time points, if you take -3, -1, where the heck?
1 and 3. Yeah.
The 3 is disappearing. 1 and 3. If you take those coefficients, that's a line, right? -3, -1, 1, 3. Same amount of space between each of those, right? So, you know, if you were to plot that on the y-axis for 4 consecutive numbers, that would look like a line, right? So this is a linear pattern. This is a linear trend. So this component is indicated linear trend. This third component is actually indicating not doing too well as far as my technical stuff here. Let's try this. This one is quadratic. And this one actually happens to be cubic. If you look at those, and you know, the numbers are off a little bit, but there's natural variability in the data. If you look at the coefficients though, you start high, you go low, you go low, you go high. So you know, that's indicating quadratic pattern. And then this one's indicating cubic, and it's pretty remarkable because it's not telling it to do that. It's just, that's what's being picked out of the data. It's saying that the average amount is the most important in terms of variability. Then the linear trend over time is the second most, and then the quadratic is the third most, and then the cubic is the fourth most. So yeah, question?
Is this something we should expect to see with most data sets, or does it just happen to be increasing in exponents here?
That's a good question. I think it's something that you will see, like if you have 4 time points, you might see it for other data sets as well, but not necessarily. There could be other data with 4 time points that won't capture polynomials. It just so happened for these data, with these data, that you saw it. And I think it could also happen with other data sets, but not necessarily.
So with other data sets, it could be like quadratic, linear, cubic, and average in that order.
It could, yeah. There's no constraint to say that it has to be the linear, you know, it has to be the average, then the linear, then quadratic, then cubic. They could go in a different order. If you go back and look at the data, the Ramus data, this is what it looks like. And you can see why, you know, we have 92% just based on the average value, because you see, you know, if a subject starts high, they tend to stay high, right? The subject that's is low, they tend to stay low, but there's growth in everybody. There is a linear growth that's also noticeable. The quadratic and cubic are less noticeable, but there are some patterns. For example, you see one subject that they're growing and then they hit a growth spurt, right? And then it tapers off a little bit. So you actually see a cubic pattern for that subject, but it's not a dominant feature in the data like the average value and the linear trend are. Okay, so the purpose of this PCA is really, it may not be as useful here as it is when you're doing data dimension, but it allows you to see patterns that you might not see readily, you know, just by looking at the data. Okay, that's any other questions on the graph? I'm going to skip over the last few slides there, but if you guys have any questions on let me know.
I have 2 quick questions about the eigenvalue stuff.
Sure.
I don't know if it was like page 27 or something, but you had like a TR parentheses statement. What does that stand for?
Was it on the slides or was it on the
in the document you were just in, I think.
Yeah, let me go get it back open here.
Somewhere between 27 and 30, I think. Yeah, that slide. The second line there, is that the trace?
Trace.
Okay.
Yeah, so the sum of the diagonal elements, right?
Okay.
Yeah, sorry, that's a good question.
No, you're good.
Okay.
And then when you were like calculating like the 2,400 something and calculating the total proportion, like the numbers were in red based on those eigenvalues, or no, in blue. Yeah, up 1 slide, 2 slides maybe. Where is that 2,405 coming from?
So that's That's the eigenvalue. That's lambda 1. Lambda 1 is the 2405. Lambda 2 would be 54.66. And so the total of the eigenvalues is the denominator. That's essentially like the measure of variability,
Yeah.
relative speaking. So lambda 1 over lambda 1 plus lambda 2 gives you the gives you the proportion of variability in the first principal component. And
Are those numbers elsewhere in the slides, or is that just the output you got from somewhere?
Yeah, that's a good question.
Okay, I was trying to add it
I
up,
didn't put
and
the
I'm like-
output, but like if I had done what I did with the Ramus data, you know, we would have the list of the eigenvalues. And so I didn't include the output. I just took it off there.
Okay, sounds good.
Yeah. Good questions. All right. So we have the next slide set is review, hopefully. I mean, some of it may be new or maybe looking at it in a slightly different way. And, you know, there's a lot of material you go through in 6612. And so the question is what's important to review? You know, that may be, people may feel differently about that, but I've over several years, come up with some ideas about, you know, how to spend 2 or 3 lectures in review. And so today we're going to talk about, you know, the linear mixed model. The notation is critical, you know, in getting that so that we're on the same page, right? And then talking about what's different in linear mixed models versus general linear models. Reviewing some of the simpler linear mixed models that you hopefully talked about in 6612. Important distributions related to the linear mixed model. General parameter estimation, maximum likelihood estimation, and restricted maximum likelihood estimation, or residual maximum likelihood estimation has you can call it either one. I like to think of it as restricted ML. So that's what we're going to talk about today. So in a mixed model, there's essentially three different formulations you can write for a mixed model. You can write it at the subject time level. So that would be like Yij, right? So Y is your outcome. I is indicating what subject it is. J is indicating time. And so you have an expression this is on the left side, and then on the right side you have, you know, beta naught plus beta 1 x1 plus beta 2 x2, and you also have the I and J indicators as well. When you have a subject level model, that's going to be Y sub I, and it's going to be a vector. So here I'm just going to put a line under it. So you can express it at the subject level and capture all of that subject's data. And then the complete data is where you stack those subject variables, or subject vectors, I should say, and you have one Y that has everything. Okay, so 3 different formulations. They're useful in different situations. The mixed model at the subject time level is useful when you want to define a specific model and talk about specific variables. When you're doing manipulation with quantities, a lot of times the subject level or the complete data level is going to be more useful. So this is what the subject level looks like. So we have Y sub I, and there's R sub I values for that subject. So we have an indicator on that because subjects may have different numbers of repeated measures. So we're just allowing for that. Xi is equal to Xi times beta. And remember, like, in terms of matrix operations, if you're going to multiply, the number of columns in the first matrix has to be the same as the number of rows in order, for that multiplication to work. It has to be P here and P here. They can't be different. Otherwise, it won't work unless you're doing like a Kronecker product. And then the same for the random effects. Z is the design matrix. B are the actual random effects that you have. And we have to have, Q has to be the same. So the number of columns in Z has to be the same as the number of rows in B for that multiplication to work. And then we have the error vector. Okay, so this is a subject level form. And I'm going to index these, even if the subjects have the same number, X and Z might be the same, but I want to keep the I on there just to indicate it's a subject level matrices. So that's basically your subject level. And our assumptions are that the random effects have a normal distribution with mean 0 and covariance matrix G. And again, if it's subject level, then G sub I, that's going to tell us that it's really going to tell us what the dimension should be for that matrix. And then the errors are also a random variable, and that vector is multivariate normal with mean 0 and covariance matrix R. Okay, so the covariance matrix for the random effects is G, covariance matrix for the errors is R. And we assume that these are independent of each other. And we also assume subjects themselves are independent. But if that doesn't hold, then we can specify the model in a little more detail and account for that. Generally speaking, G is going to be used to account for variability between subjects, and R is going to account for covariances between repeated measures within subjects. So you can think of R as a within subjects covariance matrix and G as a between subject covariance matrix. But the reality is you can add random effects and account for covariance between repeated measures that way, just by adding random intercept, random slope. As a review, if we add a random intercept and we have a simple R structure, what covariance matrix do we have for Y?
Compound symmetry.
Yep, compound symmetry. And if we have time, I'll walk through that. We'll review that that calculation or that derivation. Okay. So the last form. So you have the subject time level. You have the subject level model, and here's the complete data. We're essentially just stack those vectors. So subject 1, you have R sub 1 values for them. And then subject 2, you have R2 values for them, and so forth. You're just stacking those, and you're creating a model that you can express this way. But in terms of how you're combining subject data, this is how it looks up here. Okay, and we can write all of our random terms in one vector. So B, you stack B and then the errors. That's multivariate normal. And the mean is 0 for all of that. And then you have, we know that those are independent by definition. And so covariance between them is going to be 0. And then B has that covariance G. So that's the first diagonal matrix there. And then epsilon has covariance matrix R's, and that's the last diagonal entry of that big covariance matrix. So really, this is just, kind of rehashing some of the notation that you guys have probably seen in the past, 6612. Again, the key thing here is that there's different ways to write the mixed model, and I just want you guys to be comfortable with the different formulations, you know, at the lowest unit, at the subject time level, at the subject level, and then complete data level. And this is just some comments about why do we keep the subscript I on there? It's not only if they're different than each other for subjects, but also to capture the dimension of the matrix, right? So the big R matrix is going to have R1, R2, R3, and so forth down the diagonal. But R sub I, what's the size of that matrix? What's the size of the what is the size of R sub I? How many rows and how many columns does it have?
However many repeated measurements the person has.
Right. So it would be, I used R little r to indicate that. So it has little r sub I rows and little r sub I columns. So let's say if R sub I is 3, there's 3 measurements on the subject, then you know that covariance matrix, it's going to be a 3 by 3. It's going to have 3 columns. It's going to have 3 rows. So there's going to be 9 entries altogether for that, right? Kronecker product is something that we use to simplify expression. So the overall G matrix can be expressed as the identity matrix, an n by n identity matrix times G sub I. And what is a Kronecker product? Well, you take matrix A, and the first element, you multiply it by the entire B matrix. The second element, do the same thing, and so forth. So this is what the Kronecker product looks like. And unlike the regular product of 2 matrices, you don't have to have the number of columns in A be equal to the number of rows in B. So you can take, you know, let's say a 2 by 2 times a 5 by 5 and get a Kronecker product. And what's the dimension of that product going to be? So we have a, let's say A is 2 by 2, and we do Kronecker product, let's say 5 by 5. The resulting matrix is going to be 2 times 5 is going to be 10 by 10. Okay. And so I've used it here to show how we can go from a subject level model to a complete data model. We're going to also talk about the Kronecker product to count for repeated measures over 2 dimensions. So if you have repeated measures, let's say over time and over space, we could use the Kronecker product structure for that. And we'll talk about that in more detail, probably within the next couple weeks. If you have a random intercept model, there's a couple ways that you can write. Like we know that in mixed, if you want to specify random effects, you have the random statement. And if you want to specify the error covariance structure, you specify repeated statement. But if there's a random intercept, there's a couple ways that you can write it. You can write random intercept / subject equals ID. And you can also just say random ID. What's the difference? When you say random intercept subject equals ID, you're specifying a subject level model. Whereas when you say random ID, you're specifying a complete data model. But really, the calculation should be the same. If you're going to specify other types of random effects that are not on subjects, a lot of times you use the second approach, and you specify that variable that has that you want to identify the random effects for. Okay, so we'll see several examples of that later. As far as notation for the parameters in the mixed model, this is one way that I've seen to do it. Beta, those are the fixed effects, those are the regression coefficients, right? And so we can keep that, you know, convention. And then we can say the alpha parameters are the covariance parameters. So collectively, a mixed model has parameters theta, which contains the covariance parameters and the fixed effects, you know, the regression coefficients essentially in the model. And those are the things that we estimate using maximum likelihood estimation or restricted maximum likelihood estimation. The random effects, I'm going to use B for that. And a lot of times it's just going to be a random intercept, in which case you can take the bold off and it's just B sub I. If you have a random intercept and slope, then you can, you know, B0 is going to indicate the random intercept and B1 the random slope. So this is a key thing, is that random effects, you know, we usually say you put in a random statement to count for between subject variability, right? And you specify the repeated statement to count for repeated measures. But by adding random effects, we also account for repeated measures. So you can do that with account for repeated measures by using a combination of repeated and random statements. So we're going to talk a little bit about the random intercept model. So you have, in this model, you have our mixed model, and again, subject I, time j, some type of measurement y that we're taking, and you have a number of predictors, x1 up through xp minus 1, and coefficients for those. So that's the x beta part of the model. And here I'm just adding a random intercept for subjects. So that's the B sub I and error. So that's your basic random intercept model. And same assumptions as before. So the question is, what is the variance of y in this model? And this is something I'm going to try to walk through, see if my my pad cooperates here. Move this over, get this out of the way. So I'm going to go to this, let's pick this up. So the same model here, it's a random intercept model, and we want to find the variance of y sub I. So you can also this is synonymous with our covariance y sub I. Okay, we may call it either one. So the variance of a matrix is the same as a covariance matrix for y sub I. So just don't get thrown off by that. You could see it either way. So what we need to do initially is we're going to be taking covariance between different measurements. And so let's consider, first of all, where we have subject I and time j and subject I time j prime. Okay. So what we need to do is just express that in terms of the model that we have. So this is equal to covariance between terms of the way I've written it above. I'm not sure why it does that. It's annoying. B sub I plus, this is not going to last long if this keeps happening. I'll try pointing down a little bit more on it. See if that stays. No? Okay, and then the only difference between that and the next set is going to be that we have a J prime there. And so we do have an A, down here we have J prime. Sorry, this is one of the things that I have to figure out what's going to be efficient, what's not going to be efficient. And I figure it's going to be helpful to do some writing so you guys don't fall asleep. Okay, so the difference between the left and the right is we have J on the left and J prime on the right. And so when you take the covariance, you have to, you know, what do we know about those quantities? Well, we're going to look at all combinations. You can consider, like, when you expand out, you know, two quantities that are multiplied when you're doing algebra. We do the same thing here, but we can simplify this before we even worry about that. When you take covariance, what do we know, you know, in terms of quantities here? Some are fixed and some are not fixed, right? Which ones are fixed in a regression model?
Betas?
Betas are fixed. And we also condition on X. So we can simplify this already and just say this is equal to covariance between and so the B's and the epsilons are the things that are random. So those are the things that are going to stay in there. Okay. X beta, there's no randomness in there because in regression, there might be an X, but in regression models, you condition on X. And for frequentist models, beta is fixed. For Bayesian models, that may not be true, but you know, this is a frequentist derivation here. Okay. So this, we've reduced this quantity, right? And we want to consider this case here, the first case where J is equal to J prime. And so that quantity above becomes or you can write it this way if they're the same, right? Now, they're the same on the left and right here, right? So what is this really? Covariance between X and X. What would that be? What's another way to state that?
That's the variance between.
Exactly. Yeah, a couple people answered that, thanks. So that's the same as the variance as B sub I plus epsilon ij. Okay, now what can we do at this step here? We can apply something we know. For those that had theory,
You can break the variance into two parts.
yeah. Jonathan, why can we do that?
Because you know the distribution of the betas and the epsilons.
Yeah, we know the distribution, and more specifically,
The epsilons and the B's are independent of each
yeah,
other.
that's the thing allows us to write it as the sum. So you can write this as a variance of B sub I plus variance of epsilon ij, right? Now, if we have a random intercept, this is just going to be the variance of the random intercept term, and then the variance of the, I don't know why it does that. I have to figure this out.
Just to double check, we don't add 2 times the covariance of those because we know they're independent, correct? In the bottom line.
Yeah, that's right. So that's because of the independence that we have. So because of independence. Yay. Okay, so that's when J is equal to J prime, but looking within a subject, right? For subject I. Case where J is not equal to J prime, then we have covariance. We just write it like we had above. J prime. Okay, and here we can expand it. So we take BI times BI, so this would be covariance between BI and BI. I'll go ahead and write it out. We know that these are independent, but I'm just going to write it out so that to demonstrate how you would normally expand this type of quantity. Covariance between, you just look at all combinations, right? So BI epsilon ij prime, covariance between Eij and B sub I, and then covariance between Eij prime. So we know that that's 0, right? From our model assumptions. We know this one is 0 from our model assumptions. And what about this one here? The covariance between two errors. In this particular model, they're independent. All the epsilons are independent. So all of these, those are independent based on the model that we specified. Okay, so just looking up again, the epsilons are IID. That means they're all independent and identically distributed. Okay, so we're left with covariance between BI and BI, which is
The variance.
say again?
The variance.
The variance. So it would be sigma b squared, right? Thus, if there are 4 repeated measures, what is this variance matrix going to look like? So variance of y sub I, just going to sketch out real quick what this looks like. What we're saying really with what the derivations that we've done is down the diagonal, right, where j equals j prime, we have sigma, please stay, sigma base squared plus sigma epsilon squared. We have that down the diagonal. And then the second part we did, when j is not equal to j prime, those are different measurements on the subject, right? And so that's sigma b squared. And that's the same for any pair of measurements where j is not equal to j prime. And so I'm just going to do that. You're going to have the same thing up here. I'll just say symmetric to kind of simplify this. So that shows when you have a random intercept that you induce a compound symmetric structure for the variance of y. What's an alternative way we can get this model? What's an alternative way that I could get a model that has the same variance of y sub I, but where the model is formulated a little bit different?
You wouldn't have a random intercept. You would just have a covariant structure that's compound symmetric.
Exactly. So the alternative to get same variance of y sub I, and a lot of times we call that v sub I, is to take out the random intercept and then specify R to have the CS structure. And I'll show you in a second here why that yields the same model fit. And we'll see that when we look at the likelihood. We'll see why that is. So in a second. So the general linear model is really just a special case of the linear mixed model where you have no random effects and you specify R to have a simple structure where you have sigma squared times the identity matrix, right? So that's a really important thing to remember. They're not different modeling approaches. The GLM is a special case of the linear mixed model. And so for GLM data, you could actually use proc mix if you wanted to. There's some features in proc GLM that are nice that you don't get in mixed. You know, like if you want to get an R squared value, things like that, and some other features in the output. And it's the same for R. What would you use in R to do a linear model? It would be the LM function. And then if you want to do a linear mixed model in R, there's a couple different approaches we'll talk about later. The least squares estimator of beta in a general linear model, you can write that algebraically And you also can write the estimator of sigma squared as algebraic quantity as well. But you can't do that for linear mixed models. You use numerical methods to estimate the parameters. Okay, there's a couple data sets that you may have seen. The myostatin data is a data that has time, and it has two groups, a treatment group and control group, but the measurements are not, it's not repeated measures on subjects. There were different samples at each time point. So that's actually GLM data. There's another data set, the mouse and smoke data, that I'm not sure if you guys have seen that. I may present next time. So what's the basic difference, other than the fact that the GLM is a special case of the linear mixed model? How can you think about the inference that's done in these two types of models? Well, with the GLM, you can think of, if we want to do testing, we make an ANOVA table, right, for a linear model, and you have sources of variation, and you're breaking it down into components. Well, the linear mixed models, you really don't do that. I mean, you can think of it the same way in the special cases where the linear mixed model is a GLM, but generally, the linear mixed model, to do tests for quantities, you create approximate T or F statistics that will have T distributions or F distributions, but you have to calibrate by estimating the appropriate degrees of freedom for those quantities. And there's a number of different approaches. You can do containment, between, within, residual, Satterthwaite, Kenwood-Roger. If you don't specify anything, then there's going to be default methods that are used. But essentially, if you want to perform a test or do estimation in a mixed model, you have to come up with a quantity, a T quantity or F quantity, and get the right distribution by estimating the degrees of freedom. And we'll talk about this in more detail next week. So this is just, talking about data and models you probably covered in 6612. The random intercept models, those are sort of the models that we introduce mixed models with, whether you have one sample or multiple samples. Another data set that's, I think that's covered in 6612 is if you have crossed random effects. So you might have judges. Does anyone watch Dancing with the Stars? Like, I know that's been around a long time. You guys are probably more hip. You probably don't watch that one, but World of Dance or any show where there's multiple judges, and each judge gives a score for each dancer, right? So that would be an example of cross-random effects where you have, let's see. So you might have a situation like this where you have judge 1, 2, 3, and then you have subject or dancer. If you're doing that application, there's a number of dancers, and then you have all possible combinations. So this is a case where you're crossing these two random effects. Okay, so we could, in our model, we could put in a random effect for judge and a random effect for dancer. And there was also judge data in 6612 that you may have seen. And so when you specify the model, you would enter those separate as random effects. unless you're interested in inference for those specific judges, then you could enter it as a fixed effect as well. So important distributions in a linear mixed model, there's basically two distributions that are important. One of them is the conditional distribution of y given the random effects. And that has a normal distribution with mean x beta plus CB and covariance matrix R. And this distribution for a mixed model is important in inference for the random effects. That's what we use in inference for the random effects. And when we apply Bayes' formula, essentially, we're going to flip that around. That's what you do with Bayes' formula, right? If you want the conditional distribution of the random effects given the data, and you can write that as a function of the random effects of the data given the random effects. Okay, so this distribution is going to be important for when we do inference for the random effects, whereas the marginal distribution of y is, which we can extract from this joint distribution, has mean x beta and variance v, which is zgz transpose plus r. And just to run through that one real quick, with this marginal distribution, variance of y, that's the variance of x beta plus ZB plus error, right? And how can we simplify this again? What's the first step we do here? We think about what's random, what's not random, right? So how can we can simplify this right away? Elise, were you going to say something?
Take away the x beta term.
Yep, that's right. That's the first step. We condition on x, and we know, again, frequentist analysis, we don't consider a distribution for beta. So we can simplify this by saying ZB, right? And again, with mixed models, we know that B and epsilon are independent of each other by definition. So we can simplify this to ZB plus variance of epsilon. So that's by independence. Now, here's a question for you. If there's a constant for variance, what happens to that constant when you pull it out in front of the variance?
It's squared.
Squared, yeah. I heard a couple of you said that. I got you both. That's right. Now, the thing here, though, is that we have a matrix. So how do you square a matrix quantity? Well, you're going to pre-multiply by z and then post-multiply by z transpose. That's how you essentially square a matrix when you bring it outside of the variance, okay? So this is, let's say, squaring z, okay? And then we have variance epsilon. So variance of B. That's just G. Okay, so that's G, and then we have Z transpose. What's variance of E or epsilon?
R.
R, right. So that's how we get that quantity. So that's in general for a complete data form, variance of Y is equal to Z, G, Z transpose plus R. And that shows you why we can account for repeated measures even by just adding random effects, okay? And not just specifying the R matrix. There's a combination that we can use in order to account for repeated measures, okay? But those are the two important distributions. The distribution of Y given the random effects and the marginal distribution of Y. Those are the two distributions we're concerned about in a mixed model. That's a pretty good stopping point. There's a few slides left, and like I usually do, I can spend the first 5 or 10 minutes next time recapping. It's pretty much going to be the likelihoods, and then maximum likelihood estimation, restricted maximum likelihood estimation. You can review that, but we'll go back over it at the beginning of next time. And I will be here. I'm actually I have to take a break. So if you guys want to hang on, for those of you that want to do the office hours, you can hang on, but I'm going to take a short break and come back in about 15 minutes or so. For those that are not going to be here, again, there's also time Friday 9 to 10, and the Zoom link is on Canvas for that. It's not this link, it's a separate link. Otherwise, I'd be available for questions, some questions via email, and we'll talk on Monday. And so your homework will be due Monday. Any questions about the homework? I think I laid things out pretty well, but you're going to upload that to Canvas. Try to streamline your work as much as you can. If there's extra stuff like code or extra output, you can put it in an appendix. Any other questions? Please make it a PDF. It'll be quicker to grade if everyone converts it to PDF.
Can we use SAS or R for the homework?
Yes. And you'll notice that, this class is really, I probably emphasize SAS a little more, although I've been working on getting R up to speed and kind of so that you really have both. But you're welcome to use either one. You're welcome to use SAS or R. One software may be easier to use than another for a particular thing, but you're welcome to do either one.
Will office hours be recorded?
I'm going to try to record it. Yeah. So if you have a conflict, because somebody I think Ben had mentioned that he has a conflict, then, and I'm not sure about Yanran, but I will record mine. Okay. See you shortly for those that are going to join back on, or you can hang tight, I think, probably. I'm going to stop recording this.